Hello, AP Calc. Mr. King here. We're going to cover part 2 of our growth and decay chapter section 6.4, and we're going to begin today with the law of exponential change. This is a really key law in mathematics and especially pertinent in this day. So the law of exponential change, hope you guys can read that all right, says the following. It arises when the growth or decay of something is proportional is there to the amount of that quantity. The differential equation that leads to this is pretty simple. And it looks like this. If y is our amount, it's our quantity, and we want to know how it changes with respect to time, we say dy dt, the rate of change of y with respect to time, is equal to some proportionality constant k times y, the amount of that quantity. And there it is. The law of exponential growth and decay comes from the solution of this differential equation. K, again, is a proportionality constant. It's known as the growth or decay constant. Our book talks about K being greater than 0 always. But if K is greater than 0, typically you will know that you have, not typically, but you will have a growth exponential, and if K is less than 0, we have decay. And just let me add a little note here. This is growth when K is positive, like that. So we're going to solve this differential equation, and not surprisingly, we're going to use separation of variables. So again, we have dy dt is equal to ky. So when we separate variables, we're going to get dy over y, k dt, like so. And if we integrate or anti-differentiate, we see we get the familiar natural log, the absolute value of y is equal to kt plus, and I'm going to call that c1 instead of c. Sometimes it doesn't matter, but we're going to do that here. And the next step, we're getting used to this now, right, is we're going to exponentiate each side. That will give us the absolute value of y is equal to e to the c1. I'm just changing the order here. Remember, e to the kt plus c1 can be written as e to the c1 times e to the kt, like so. And we want to get rid of this absolute value on the left. And so typically what we do is this. We say, well, you know, y could be plus a positive or negative quantity, and that means the left side would always be non-negative. Now, if you look at the right side, e to the c is always non-negative, and e to the kt is also always non-negative, which is kind of interesting. So going forward, we drop the sticks, as it were, and we say y is equal to plus or minus e to the c1. And e to the c1 really is our constant, isn't it? And times e to the kt. We're going to let a equal plus or minus e to the c1. And we'll do a change of variable here on that. And we've got y is equal to a e to the kt, and this should be very familiar to all of you. That's an exponential function. With base e, the natural base. Now in these problems, A represents the amount present when t equals 0. I'm sure you've encountered this when you've done radioactivity problems in a science course or in a math course. A is often also known as Y0 or Y naught, the initial amount. So let's look at an example. Our law of exponential change can look like this in a general sense. And if we think about a radioactive decay problem, well, we know that k will be less than 0, don't we? Because it has to be an exponential that decreases as time increases. Okay. Another kind of application here is if we have continuous compounding of money in an account. But again, let's look at radioactive decay. I think I've got an example right here. This is a very straightforward example that won't be too challenging. So let's say k is equal to negative 0.5. So this will be decay. And let's say that y of 0, another way to say y naught, is 200. Well, we can quickly write our law of exponential change for this substance, or whatever it is. So y is equal to 200 e to the negative 0.5 t. And there's our decay exponential. So if we were to graph this, if t were 0, we see we get 200. And so on our y-axis right here, and here's our time axis, we're going to start up here. And then over time, this is going to decay like that. In physics, you might be told that dy dt is equal to negative ky. And this sort of is slightly different from what we started with, where we just let k be k. Sort of tells us right away that this is something that's going to decay over time. But because we have the negative in front of the k in this case has to be a number that's greater than 0. Well, we know that this has the solution that y will be equal to y0 or y naught equals e to the negative k t, where k is greater than 0. Law of exponential change. When it comes to radioactivity, we have a particular definition which is familiar to you, I'm sure. And it says the following. The half-life of a substance, you could say of a radioactive substance, is the time that it takes for half of the nuclei of the substance to decay. And that assumes we start with a fixed amount of a radioactive substance. You could start with 10 grams, and if it took, say, 10 days for that to turn into 5 grams of that radioactive substance, the half-life Did I say 5 days or 10? If it took 5 days, so let's go back to 10. If it took 10 days, then 10 days would be the half-life. So we'd go from 10 grams to 5 grams in 10 days. Now I see why I got confused there. Sorry about that. Okay, now we're going to do an example that's it's out of our text. And this is on page 357 if you wanted to see the problem. There's not a terrible amount of information there. And the basics are as follows. We're going to look at neptunium. This is our radioactive substance. I believe it. Let's write that nice. It has the symbol NP 240. Those of you who've studied chemistry more recently than I have, please don't make fun of me if I didn't write neptunium right. Is it one capital and one small p, or is it both capitals? I have no idea. I don't remember. So neptunium has a half-life of 65 minutes, a little bit over an hour. A very short half-life. If dy dt is equal to negative ky, describes how this radioactive material decays, where t is in minutes, let's build a function and let's make an equation using that function, and let's see if we can figure out what k is. We have enough information here to do this. And so what we're going to write now is this. We know that the law of exponential change tells us that from dy dt equals negative ky, we have this equation that results, that solves that differential equation. Now, if we're looking for half-life, we know that y over here is 1/2 of the original amount, y0. And we're looking for k, but we know that the time is 65 minutes, don't we? So we can multiply by 65 there. So in this problem, what's interesting is we don't really need to know, we don't even care how much y0 was. We just know that we want to know how long it takes to get to 1/2 of y0. So y0 could be anything. Those divide on each side to 1, leaving us with 1/2 is equal to e to the negative 65k. And now we have a fairly trivial equation to solve. And without showing all the steps, it leads to this. I know you know how to do this. That k is equal to the natural log of 2 divided by 65. And this happens to be about 0.01066. And that's the decay constant. Now it turns out, and this is something you guys want to remember, this is how you find a decay constant in our course.